Okay, so similar to the previous test, I'm going to go ahead and make a video version of the review. I will be making it in short bite-sized pieces. So this first video is just going to go over the very first two questions, kind of old stuff dealing with law of sines, law of cosines, as well as area formulas. Before we start that though, we need to talk about something. So remember, when you have a triangle like this, ABC, not written to be particularly to scale or anything like that, but anytime you have an angle, the side across from it, remember, is named by the lowercase value. And so like opposite capital B is little b. And you should know that, but just making sure. So we have the law of sines, which states that the sine of angle A divided by A is the same as B over B or C over C. And sometimes instead of using A, we could use alpha for the angle. Instead of B, we could use beta. Instead of C, we could use gamma, but they mean the same thing. And what you want to remember is this is useful on ASA triangles. Notice you have lots of angles there on one side. AAS triangles. And then remember, this is the one that's the scary one that is the ambiguous case that sometimes has two triangles and sometimes does not. Another formula that's a little harder to deal with. Remember, it looks kind of like the Pythagorean theorem, at least it's the beginning, but they all have this pattern that the sum of any two sides squared is going to be the third side, but with a little qualifier, because if it's not a right triangle, you need extra information that's outside the Pythagorean theorem right here. This is called the law of cosines, and it is very, very useful on side triangles, side angle, side triangles, and of course, you can also use it on SSA triangles. That's the ASS effectively. Now, in terms of area formulas, we had three of them. One of them is that if you have the product of any two sides, like A and B, which are side by side, 1/2 A times B times the sine of the angle in the middle would give you that area. Or 1/2 B times C, again, they're right together, times the sine of the angle in the middle. Three different renditions, but every single time it's 1/2 the product of any two sides times the sine of the angle in between them. This one was the one we called Heron's formula, where if you have all three sides, you can go ahead and find the semi-perimeter by adding the three sides together and dividing by 2. That's going to be your semi-perimeter. Excuse me. And then the semi-perimeter, and then the product of that semi-perimeter with S minus A, S minus B, and S minus C. So without any further ado, I'm going to have this sitting off to the side for notes as we go through it, but let's go ahead and try to solve this first triangle. So the first thing I'm going to do is I'm just going to draw a random triangle. I'm going to call this A, which makes 2 right here. I'm going to make this side B, which is going to make this little guy 3. This is the symbol gamma, which is a fancy way of saying C, or 60 degrees. Now, what you'll notice, I hope at least, is that you're looking at an SAS triangle. And as I mentioned a moment ago, that's going to use the law of cosines. So if I'm looking for C, the formula said C squared equals A squared plus B squared minus 2AB cosine C, or gamma. Now, I don't always write the formula down on these because it is kind of lengthy, but this first time I decided to do that. So A squared would be 9, B squared is 4, 2 times 3 times 2 times the cosine of 60 degrees. Now, in this particular instance, that's actually kind of nice because you'll notice that there's all simple numbers. And so as long as my calculator is in degree mode, I should be able to type that in exactly as it phrases. So I've got 9 plus 4 minus 2 times 3 times 2 times the cosine of 60. Now, all of that became a pretty nice number. So I just got that C squared is 7, which makes C the square root of 7. Now, normally I would say plus or minus root 7, but in this particular instance, the minus would not make sense. Now, on the test, rather than asking you to solve for the whole thing, I'm going to ask you to solve for some pieces. So I just found one of the pieces right here as being root 7. Now, as far as finding the other piece, maybe beta, maybe I'll use the law of sines. I could say that the sine of beta divided by 3, because that's what I'm looking for, would be the same as, let's say, the sine of 60. That's something that I know right now, over root 7. So with a little bit of cross multiplication, I could say that the sine of the angle beta is 3 times the sine of 60 divided by root 7. So I'm going to do that. So let's see, 3 sine 60 divided by root 7 is going to give me a strange little decimal. It's not a big deal. And then I'm going to take the inverse sine of that value, and I found it that the angle beta is 79.106 degrees. And we are done with the first problem. Now, on the second problem, I didn't ask you to go quite so far. We're just going to go ahead and find one value. So again, drawing a quick triangle. Here's A, B, C. I know that A is 7, B is 5, and C is 8. That's a side-side-side triangle. So again, we're going to go back to that law of cosines. But what I always do is I line up what I'm after and how it's across from each other. So notice I did the same thing up here. C was across from C. And that's kind of the idea. So what I'm going to do is then I'm going to say that 5 squared is equal to the sum of the other two guys squared minus 2 times 7 and an 8, and then the cosine of the angle in the middle, which is angle beta. Now, I have found that historically a lot of students get themselves into a little bit of a hot water here because they come in and they make a little bit of a mistake in right here. So I'm just going to take 2 times 7 times 8, and I got negative 112 cosine beta. And I'm going to choose to write a few steps that I would not necessarily always do because you can do this problem quicker. But I'm going to take 25 and take away 49 and take away 64. Looks to me like I'm down to negative 88. Let's divide both sides by negative 112. And I'm down to 0.786. And now you'll notice that I never clear my calculator. And then if I take the inverse cosine to get the angle, I found out that the angle beta is 38.213 degrees. So that's awesome. We're kind of done with that. So those are the first two. Now I'm actually going to jump down here and look at D next. And I know that's out of order. So if you're a little OCD, my apologies. But this problem is actually the easier problem and this one's the harder one. So for part, again, A, B, C, it says B is 8, it says alpha is 56, gamma is 41. That to me looks like an ASA triangle. And so I can certainly use the law of sines to find pieces that I want. And I automatically can see that since I have two of the angles, I could say that 56 plus 41 adds up to 97. So if I took that out, I know that the measure of this one up top here is 83 degrees. And therefore I could say that the sine of 83 divided by the side across from it is the same as the sine of angle C divided by the side that's across from it. This problem comes out really, really nice and easy. So here we go. 8 sine 41 divided by the sine of 83. And that's going to give me C. And so I found that my value C right here is 5.288. And I'm done. Now, of course, not big surprise that the one problem in this whole mess that I actually waited on till last is the angle side-side. It's something that we stressed in class. I waited a day on it to make sure that we could really stress it. That's this case right here. So when we look at this and you decide to call this A, and again, you could put A wherever you want. That's just where I like it. I like to put B right there. We're going to put this as B therefore. And this is going to be C. Now, remember, you have to decide, is it possible that this 6 could have swung inside right here? And I think some of you already probably realize that it could do that. So I think we're going to have two options. One of those options looks like this big triangle, and one of them is going to slide to the inside. But we're going to find out if that's true as we work. So let's use the law of sines, which says the sine of b over 8 is equal to the sine of 35 over 6. I'm going to do a little cross multiply. So 8 sines of 35 divided by 6. So the sine of beta is this. So if I took the inverse sine, then I found that my first answer for beta is 49.886 degrees. That's 49.886 degrees. Now, I'm going to store that as B because I'm going to use that again. Now, if we did that, then that actually means that the angle C that would go with that would be 95 degrees. So this guy up here is 95.11 degrees. Well, nothing seems to be all that bad yet. But look what happens when we come over to here. The rule that I gave you is if there is a second triangle, we could take that first angle that we had and take it away from 180. And so according to the mathematics, that would make this 130.11 degrees. And as it turns out in this particular instance, those are fine. They add up to less than 180 degrees. So that's 100% plausible that that answer would be there. And so the only thing I would have left to do is add that to 35 and take away from 180 to find that top angle of 14 degrees. And for the sake of brevity, I'm not going to do all of this, but to find C, I would do the law of sines one more time. So for this problem, I would say then that the sine of 35 over 6 is the sine of 14 over C. And then I'm going to go ahead and finish solving that. And I want to remind you really quick that we do actually have an option right here to look at a program that I showed you. So I just did a Google search on Triangle Solver, and this is my favorite one, Project Nayuki. And so, for example, the problem that we were just looking at had a side of A was 6, side B was 8. Now, this doesn't help you for the test, but it does help you to prepare for the test. And what do you know? When I did my problem, I got two angles for beta at 49.8 degrees and 130.1 degrees. So it tells me I did okay. And then the side C that we started on, I kind of got finished up with this one, but those are the two values for side C. And that kind of finishes up that problem. Now, the rest of the story comes in number 2, and that's as far as this video is going to go. It's just like, what's the area of these particular things? So what we're going to do is we're going to use those formulas that we had a moment ago, and let's find the area of each triangle. Well, the first triangle says if you have two sides and the angle in the middle, then all I needed to do is do 1/2 the product of those two sides times the sine of the angle in the middle. And this is a nice little unit circle problem done on purpose, but honestly, right now, if we just grabbed a decimal, I'm okay with that. We're going to get 2.598 would be the area. But if you wanted to notice that half of 2 is 1 times 3 is 3, and the sine of 60 is √3/2. And you'll notice that 3 times the square root of 3/2 is, in fact, 2.598. So those are two very good answers. Now, for part B, you'll notice this is one of those problems where I actually gave you all three sides. So when I get all three sides, I personally like to use that Heron's formula. So if I look at 5 and 8 is 13 plus 7 is 20. So that makes my semi-perimeter 10. So Heron's formula says, let's take my semi-perimeter. I'm going to take my semi-perimeter minus A, which was 7. So 10 minus 7, 10 minus 5, and 10 minus 2. That's 300 inside of there, which is 10 square roots of 3. And it's really nice and easy value. Now, the last one that I thought it would be worth looking at, and I'm just, again, trying to keep the video relatively short, but I'll look at D. Now, keep in mind, since C had two answers, there were two values you could get, but you can do it the same way I'm going to do on this other one. But by the time I finished, I, in fact, did have two sides and an angle in the middle. So 1/2 the product of the two sides times the sine of the angle in the middle. And so here we are, 0.5 times 8 times 5.288, sines of 41. And I messed up in there somewhere, got an extra parentheses, and it had an area of 13.877. And that's literally how to do those problems. But again, you can double check your answer using Project Nayuki. Hopefully that's going to help you out. Let me know if you have any questions. I will post an answer key. Bye-bye.